everyone, and in this we're going to be looking at two exam questions from the 2011 SACE Mathematical Studies examination. So we're going to be looking at question 15 and question 17. If you want to follow along with them, you can get a copy of the exam booklet and we'll go through them together. So the first one's looking at systems of linear equations and how we can utilise them, and question 17, which we're going to look at a bit later, is about developing and proving a conjecture through the use of calculus, tangents and normals, which is going to be a bit of fun. So hopefully you can follow along with this video. If you have any questions again with any of this video, leave them in the comments section below and I'll answer them as soon as I can. But let's get started. So question 15. Look at the metal rod in the diagram. One end is fixed at 0 degrees and the other end is fixed at 100 degrees Celsius. And heat is conducted along the rod, and there's no significant temperature loss at each point. Okay, they're equally spaced, these points. We have A through to E, so we have 5 of them, and they're all equally spaced, so we're told that much. The constant temperatures at points B, C, and D can be found using the fact that the constant temperature at each point is equal to the average temperature of the temperatures of its two neighbouring points. Very important point, because we're going to have to develop a system of equations to solve. So that's going to be a very important piece of information which we'll come back to in just a moment. So let x, y, and z represent the constant temperature at the points B, C, and D respectively. So for 1 mark, nice and simple way to start off this system of linear equations, we need to show that the following equation can be determined by considering the constant temperature at point D. So we're looking at the temperature at D, and it's equal to the average of the temperatures at C and E. We remember that from this fact here, this important bit in italics. It's always very important to read the question, because that's going to be a key piece of information. So we know that the temperature at C is going to be the temperature at Y, because we know X, Y, and Z are B, C, and D respectively. So we know that the temperature at C is going to be Y. Then we know the temperature at E is going to be 100, because we know that one end of the rod is 0, the other end of the rod is 100. So, from there, we know that Z, which is the temperature at D, is equal to Y, temperature at C, plus 100, temperature at E, divided by 2. So we multiply both sides by 2, so we get 2z equals y plus 100, because of course it's going to be nasty working with a system of linear equations and having fractions involved. So keep it simple, multiply both sides by 2, so bring the 2 up to the other side. It's the same sort of process. And what we do from rearranging is we find that negative y plus 2z equals 100, like it asked us to find. And it's very important we have it in this form, because x, y, and z are unknowns, and we want to develop an augmented matrix so we can solve and find out all these temperatures along the rod, which is something that we can do in just a moment. But first off, we need 2 additional equations, of course, because we have 3 unknowns. We need 3 equations in order to solve what we need to know, which are x, y, and z. So, similar approach. What's the temperature at B? Well, we know temperature at A is 0. Temperature at C is going to be, obviously, equal to y. So 0 plus y divided by 2 is x, which is the temperature at B. We rearrange this. Again, we multiply both sides by 2, so we don't have to work with any fractions. And then we get it in terms of having x and y's on the same side of the equation. So we end up with 2x take y equals 0 from that equation there. Hopefully you can see it's just an average. Rearranging, it's exactly what I did in the last part, except now we have 0 instead of the place of 100, so it's going to be equal to 0. Okay, so now let's have a look at the temperature at C, which is the average of B and D. So we know that's x, that's y, and that's z. So y is going to equal x plus z, sorry, not z. I should get out that American habit there. But x plus z divided by 2 is equal to y, which we have here. It's just the average. So again, from that very important bit of information in italics, we get that. Multiply both sides by 2, so we don't have any fractions. Rearrange such that x, y, and z are all on the same side of the equation, and we end up with that expression. Because we have no numbers involved, that's equal to 0. So, as you can see there, we've set up a system of linear equations. We now have 3 equations, 3 unknowns. Hopefully that was easy to follow. We're just using this little bit of information here, and we're letting x, y, and z be obviously B, C, and D respectively, is given in the question. So there is a bit of interpretation here, so it's very important that you understand conceptually what's going on. And the best way to understand this kind of thing is to get practice. So practice doing your stats questions in particular, because they require you understanding the question, understanding the context. This is an example of a non-stats question where you need to know context as well. So let's go on to our next part, because I think I've explained that reasonably well. If you have any questions, again, leave them below. We want to find the constant temperatures at point B, C, and D. Well, we know our three equations from the previous page. There should be an extra 0 there, though. But that doesn't matter. Just imagine that there's an extra 0 there that I obviously forgot to add while I was writing it out. Oh well, what we can do is, because this is only worth 1 mark, we don't want to be using row operations and all that tediousness just for 1 mark. So we use our calculator, and depending on whether you have the TI or Casio, there are different instructions. But what you need to do is you essentially need to go into your matrix app, whatever you have, put in the numbers, and then augment the matrix and get it into reduced row echelon form. Hopefully you know how to do that. If you don't know how to do that, then it's probably best to A, consult your teacher, or B, I'm pretty sure I've done it in a video once before when I was developing the Math Studies series of videos. So I think I've shown it in a couple. Check it out. I might be wrong, maybe I've forgotten, but what we get from this as a consequence of solving this matrix using technology is x equal to 25, which is the temperature at B. So I should probably write equals temp at B there, but that's just a little detail. Y equals 50 degrees Celsius, which is the temperature at C, and Z equals 75 degrees Celsius, which is the temperature at D. And in this case, actually really makes sense when you consider what was happening before, because we have, I'll just use this rod because it's the same sort of thing, but now we're looking at a slightly different context. We have 0 there, and if we have 50 there, then the average of that is 25. 25, 75, the average of that is 50. So yes, it does fit. It is a reasonable idea. You need to have a reasonable idea of what the answer could be when solving a question. Otherwise, if you get something completely wrong, you're just going to be marked down for it, and that's not good. So check it. And in this particular context, this actually makes sense. So now suppose it's not 0 at the end. Suppose it's p degrees, not 0 anymore. Well, let's develop a new set of equations, assuming that that's p instead of 0. So temperature at A is p degrees Celsius, right? Well, we want to know the temperature at B, so we have P plus Y, again we're using X, Y, and Z, and then from there we get 2x take Y equals P. Now, it doesn't equal 0 like it did before in the previous system. So again, we can use our previous results because the temperature at B is the only one that depends on P, the others depend on each other. So we can just use the previous results obtained, which are x take 2y plus z equals 0, and negative y plus 2z equals 100, because they don't rely on P. Only the temperature at B relies on P. Hopefully you can see that, because we're taking 2 points next to each other. And hence we get that system of equations that we were asked to show. Okay, so now we're doing it for where there is no 0 degrees, but P degrees, which is unknown. So we're asked to use clearly defined row operations to solve this system of equations for temperatures x, y, and z. So first off, I'm going to swap row 2 and row 1, because it's going to make it easier in the long run. So go ahead and swap them. Again, hopefully you know how to do row operations. Then the next part is to go R2 and what we put in row 2 is put in row 2 take to row 1. Again, what we ideally want is to try and get some zeros in the bottom there. Such that we can actually get, say, y or temperature z out of the equation in terms of P. Of course, everything's going to be in terms of P because we have that reliance on y, and y has a reliance on z, and z has a reliance on x. So it's always going to be traced back to P. So everything's going to be in terms of P. But ideally what we want to do is we want to start getting more zeros. So that's the approach I've taken here. And now row 3, what we're going to put in row 3 is row 2 plus row 3. And what we get from that, as you can see there, are 2 zeros. So what we end up with is 2y equals P plus 100, just by considering that system of equations. So hopefully it makes sense. It might not be obvious, but again, just try and look for ways that you can get a single variable on its own. And in this case, it isn't z that I've isolated. I've isolated y. It doesn't matter. Just get one on its own. Look for that. Swap rows if you have to. Subtract rows, add rows. Just get zeros there. This is purely just an exercise in algebra. That should always remember how you can do that whenever you're solving a system of linear equations by hand. So 2y equals p plus 100. And therefore, we divide by 2, and we get y equals p plus 100 on 2. Excellent. Now we know from our previous set of equations that 2x take y equals p. That was one we explored before on the previous page, the previous question, the 2 marked one. And therefore what we get is 2x equals p plus 100 on 2. So, what we're going to do is we're going to essentially write this over a denominator here, so it's going to be 2p on 2 there. By doing so, hopefully understand I'm just multiplying that p by 1, which is 2 on 2, so 2p on 2 there. But then we're dividing by 2 as well, so it's going to be all over 4. So the final result of doing that little algebra, hopefully you can see where I went there, is 3p plus 100 on 4 for x. And now 2z equals 100 plus p plus 100 on 2, because negative y equals, negative y plus 2z equals 100. So I bring the y to the other side and we have 100 plus y equals 2z. Again, using that little algebra, we can rewrite that equation such that it's over 2, so it's going to be 200 on 2, for example, and we have 200 plus 100, that makes 300. 300 plus p on 2 is 2z, but then we bring the 2 down to the other side and we get divided by 4. And hence we have x, y, and z, which are the temperatures at B, C, and D respectively, as a consequence of solving that system of linear equations. Hopefully that wasn't too hard to follow, it's just a bit of algebra. Rewind it, play it through until you get it, that's my advice. Again, this is a conceptual question, it's a pretty good one actually, it's a good challenge. B is 55 degrees Celsius, hence what we know is that the temperature at B is going to be equal to, obviously, x, right, from memory, yep, x, and therefore we set that equal to 55, and it's just a matter of rearranging to solve for P, because we want to know that fixed temperature at P. So 3P plus 100 equals 55, and we times that by 4 by bringing 4 up to the other side. We then subtract 100 off, and we get 3P equals 120, hence P equals 40. So the fixed temperature at that end P of that rod that we saw is 40 degrees Celsius. Okay, question 17 now. This is a conjecture question. This is a good one, so let's dive straight in. So we're given our f of x as being k plus k on x, and we're given the graph there, 4k equals 1. The tangent and the normal to the graph at the point where x equals 1 also solved. So we have the tangent there, and then we have the normal. So we're asked to estimate the x-coordinate at the point where the normal to the graph y equals f of x at the point where x equals 1 intersects the graph. So we're looking at x equals 1, we're looking at the normal, so it's this one, because we have the tangent x, we can see we've got decreasing slopes, so the normal is that one, and we can see it intersects f of x again right there. So the normal appears to intersect the graph of x equals negative 1. Do the same for this time k equals 2, so imagine there's a 2 in there both times, look for where normal intersects, and you can see it's roughly an x-coordinate of negative 4. Going on to the other side, we write that down because that's what was asked. And then we consider when k equals 3, at the point where x equals 1. We have the equation x take 3y equals negative 17, and that equation is the normal of the graph. And what we want to do is we want to find an x-coordinate point where the normal intersects the graph again. Well, obviously, they're going to both have the same y value, the same y-coordinate when they intersect. Okay? So what we can do is we can set 3 plus 3 on x, which is the value of y, if we substitute in k equals 3, and we put that in the place of y for our normal equation, and we get this, x take 3 lots of 3 plus 3 on x is equal to negative 17. Now we can expand this out, so we got, negative 9 take 9 on x, sorry, And then what we'd need to do is, because we have a denominator term of x, if we want to solve this as a quadratic, we have to multiply through by x and then rearrange and use the quadratic formula. But at this point, the question's only worth 2 marks. So my advice is to say, well, okay, they share a y-coordinate, we put that into the formula, and hence we can use our graphics calculator to graph the two functions. You could rearrange that for y quite easy, and we know that that's y equals that. And we can find that x equals -9. So it's up to you, but the way I do it is to say they share the same y-coordinate, and hence using technology we get x equals -9. So only ask to find, it doesn't ask to show all those sorts of words, so save some time and do it that way. Okay, so now what we do is we summarize our results. So we have the x-coordinate at the point where the normal to the graph of the y equals f of x, at a point where x equals -1 intersects the graph again. Well, we have -1, -4, and -9. For k equals 1, k equals 2, k equals 3. So you can see we're starting to build up a conjecture here. They're getting us to think of a few ideas. So now, what is our conjecture? So on the basis of these results, the following incomplete conjecture is made. For f of x equals k plus k on x, normal to the graph of y equals f of x at a point where x equals 1 intersects the graph again at a single point, and the y-coordinate of that, the x-coordinate of that single point is x equals, okay, so we need to look for a relationship here. So we have k equals 1, -1, okay? 2, -4. Okay, well we know that 2 squared is 4, right? And we know that 3 squared is 9. So we're looking at the numbers squaring here, but not just squaring with k, negative squaring, because we always have a negative out the front. And so from that, it's just a matter of sort of seeing that pattern there, in order to make this conjecture here, that we have -k squared. Okay. So now, oh, that went a bit small. We're asked to prove or disprove this conjecture found in Part D. This is a 6-mark question, and a bit of algebra, so I recommend, hanging in there. If you have any questions about what's ahead, because it does get a little bit complex in some parts, then let me know. So, prove or disprove the conjecture made in Part D. We have f of x is equal to k plus k on x. I've just written that as to the power of -1, that x, because, 1 on x is obviously the same as x to the -1, doesn't really matter. What we do is we differentiate it using the power rule. I'm not going to go through how to differentiate it, but that constant k goes to 0, and then we bring the exponent, and yes, you've got it. Hopefully you know the power rule. If you don't, you should be worried if you're revising for your exam. And hence we get that the slope of the tangent when x equals 1 is, and we just consider plugging x equals 1 into the f prime of x, because we know that the f prime of x is the slope of the tangent. And we know that x equals 1, so we put in 1 there, so it's going to be -k on 1 squared, which is the same as -k, because 1 squared's obviously 1. Okay, so the y-coordinate at x equals 1, we put in a 1 there, right? Because we're looking at the y-coordinate when x equals 1, so we're looking at the original function f of x, and that's going to be k divided by 1 plus k, which is going to be 2k, because k divided by 1 is just k. So now what we do is we're essentially building up here. We've got our f prime of x, we've got our f of x. We're proving this conjecture by getting all the tangent details so we can get the normal details. Because what we're ultimately doing is we're looking and we're considering, well, okay, we have that curve, right? We have a tangent there. That tangent has a slope that's related to normal. We want to find when the normal intersects the graph again. So if we find the equation of the normal, and the equation of the normal is based on the point where the tangent and the curve meet, the f prime of x and the f of x meet, there's a unique point there that's also normal going through. They're all going to share that same point, and from there we get the equation of the normal, and from the equation of the normal we need to find where that normal meets the curve again. So you've got to have an equation to the function you want meeting a curve, and the only way you can get an equation of the normal is to find the equation of the tangent. So you've got to think of these ideas when proving the conjecture. This one is not straightforward, it is very open-ended, so you've got to be a problem solver. And the best way to do that is to think, well, what do they want me to find? And what they want you to find is they want you to find and prove your conjecture You need to know, you need to find essentially when the normal rejoins occur. So you've got to work backwards. Hopefully this makes sense. It might not be obvious at first, but just keep thinking, what do they want me to find? How can I get the information necessary for me to be able to find them? That's why this is a difficult question, but you need practice with conjecture questions. This is why they are, at the end of the exam, they're the most challenging, but if you show them, you demonstrate higher order mathematical skills and abilities. Hence, at the point 1, 2k, the slope of the tangent is negative k. We've concluded that because we've considered the slope of the tangent when x equals 1, and we've considered the y-coordinate x equals 1. So, hopefully you understand why I'm going through this process, because I think I explained it reasonably well just then. And now we can find the slope of the normal. And the slope of the normal is the negative reciprocal of the slope of the tangent. So we have negative lots of negative 1 on k, because we take the negative reciprocal, and we have negative k before. So we get 1 on k as the slope of the normal. So now we find the equation of the normal. So we set y take the y-coordinate and x take the x-coordinate is equal to 1 on k. Of course, they all share that unique point, which we found as being 1, 2k, because that's what the f of x has, what the f prime of x has, and of course the normal's going to pass through that same point. They're all going to pass through that same point. Hence we get that. Now y take 2k is equal to 1 on k, x take 1 on k. What we're going to do is we're going to try and get rid of all the fractions. Just get rid of them, because otherwise algebra is going to be nasty. So the best way to do it is to multiply both sides by k. So what we end up with is ky take 2k squared is equal to x take 1. We're getting rid of those k's by multiplying both sides by k, and k on k cancels out. That's what we're doing. So now what we do is we can just, get it into a form that we're happy with, and we've got the equation of the normal. And it's got k constants and x is floating around and y, but don't worry, because what we need to do now is we just need to consider the same logic that we applied in the previous 2-mark question. You remember that 2-mark question, the one which I said to use on your calculator? Well, in order to find when the normal intersects a function again, of y equals k plus k on x, we need to substitute in a unique point for both of those functions. So obviously, we're going to substitute in y equals k plus k on x, because that's the y-coordinate of the function, our original function f of x, and of course, that's going to be the y-coordinate of where our normal meets it again, right? Hopefully you follow that. So we've got ky here, so we substitute in y, and that's why I put it in that slightly nicer form, so I can put y in easy. We've got k, lots of k plus k on x, is equal to x take 1 plus 2k squared from before, when we just multiplied through by k, and we brought that to the other side, etc., etc. And now what we do is we expand out this bracket, and you see that it's divide by x. So we're going to have to times both sides by x, so we can get a quadratic out of this. And getting a quadratic out of this makes sense, right? Because just think about the original graph. We have it meeting at a point, we have it meeting at another point, but then that linear function doesn't look like it's ever going to touch f of x again, so there's probably 2 solutions. And that's where you need to sort of apply those higher order thinking skills when problem solving. So multiply through by x so that we can get a quadratic. That's very important, because we can't solve anything in this form. We can't solve anything where we have a divide by x there. So the best way to get rid of that divide by x is to times by x on both sides. So hopefully that sort of makes sense. These ideas of using algebraic manipulation to your advantage will hopefully be something that when you practice will come across as being second nature. So once we've done that, we end up with this monstrosity. As you can see, I've just put things on either side and set that equal to 0. Rearranged algebraically, pluses become minuses, that sort of thing, etc. And we're moving from the left-hand side to right-hand side and vice versa after multiplying through by x. And as you can see, we've got an x squared term. And now over to the last bit. And the last bit is where it gets a little bit freaky. Just hold your hats. But with our quadratic, what we want to do is we want to get our x terms to get our x squared, our x and our constant terms all in the same position. So that's just a matter of collecting like terms. You've probably done that before, year 10, year 11, so I'm not going to explain that in too much detail. But now we just need to consider, and this is where you really have the A grade or A plus grade understanding, how to put that quadratic, how to factorize that thing. It's not immediately obvious, but consider how to get the constant term. So obviously, when you're doing a FOIL brackets with a x squared term, you know that you're going to have an x in every term except for when you do the outside ones, right? So we know that that's going to be, that there is going to be the constant. But what we also know is we've got k squared take 1. So we know that we're going to have plus k squared x and take x as well. So it's really just a matter of analysing this form and thinking a little bit logically. And I know that's difficult for me to say because, well, I've had a bit more practice with mathematics than most people. But it comes with just thinking about it. Look at this form, consider what happens when you expand out the FOIL brackets, and from there try and get a form. That's the most important thing to do. From this form we can see that, okay, either that expression is going to be 0 or that expression is going to be 0 for that to be true. So if we let that be 0, then x plus k squared equals 0, then x equals negative k squared. Yay! Yay, we just proved it. Can you see that there? Yeah, that's awesome. And now we have x take 1 equals 0. Well, we know x equals 1 was the original point where it actually had the normal from, so of course that's going to be a solution. So we've actually checked the validity of our answer here because we got 1 out. Because we got 1 out, we know this is correct. And we've proven our conjecture, so hence it cuts the graph again, x equals negative k squared. Conjecture's proven. Hopefully this video makes a bit of sense. If not, as I said numerous times throughout this video, these are challenging questions. If you have any specific comments, leave them below.